Union AI is a, oh, there we are. Union AI is a startup. Yeah. There you go. Technical difficulties. Yeah, so we're essentially trying to build AI and data infrastructure to help organizations, companies, teams get value from their data. Because fundamentally, AI is about data. It's about harnessing that data to produce artifacts that you can then use for prediction, forecasting, large language models at this point for producing content. I'm also an open source creator. So one of the libraries that I created about 4 years ago was it's called Pandera. This is if you've ever used the Pandas data frame library, this is essentially a data frame validation toolkit that allows you to essentially add types to your data frames. So if you've ever worked with these things, it's just like this table, right, that can contain anything. So Pandera allows you to state what columns are in that data frame, what types they are, and other constraints. So little sidebar there. More recently, I created a library called Union ML, which is essentially a thin wrapper on top of Flyte. Flyte is the topic of this talk. So Union ML essentially turns Flyte into something a little bit more machine learning centric, whereas as you will learn just now, Flyte can be used for machine learning, but it can also be used for data engineering and analytics and any sort of orchestration, which is a term I'll dig into later. One of the core maintainers of Flyte, obviously, and my background is actually in biology and public health, and I kind of stumbled into data science and machine learning through my public health grad program, started taking some stats classes, and kind of fell in love with coding. It's just the process of creating with code and doing cool stuff, and feels like a superpower being able to grab data from anywhere, and especially with machine learning and other heuristics and techniques, you can do a lot of cool stuff. So these days, my mission is to build open source tools that make data science and machine learning practitioners more productive, help them build things more efficiently in a, basically a better methods for doing what we do. So I think it's worth kind of just sharing my journey, since probably everyone in this room has their own journey. So you might have come from a traditional CS background, you might have come from a science background or math background, or completely something else like theater or music. I've met plenty of folks who have come from all sorts of walks of life. So my particular journey starts in 2012. I learned Python and R kind of in tandem in grad school, picked up a little JavaScript to do some web stuff. And then around 2015 was when I got my first industry job as a data scientist. That's where I kind of learned more of the data science specific tooling like pandas and sklearn. And if any of these logos make sense to you, if you recognize them, right? You see SQL and Keras and Dask and PyTorch. And so this is kind of like just a sampling of the various tools that I kind of added to my tool belt as I continued to work in industry. Around 2020 is when I joined Union AI, essentially the Flyte, one of the core maintainers and core contributors to the Flyte project. And that's when I really started to understand, and I was kind of moving this direction anyway. And so started to understand machine learning systems. So like the model itself is just a small part of the entire kind of supply chain of data, and then the endpoints that you might deploy to, and how do you handle when data changes. And I'll kind of get into this, but I'm just hinting at it here, where working on the algorithms is cool work, writing papers, implementing papers and stuff like that. But when it comes to implementing stuff and shipping stuff in a kind of industry context, it's also important to understand the business needs. And so there's a whole chain there that needs to happen as a practitioner that might not be an expert in kind of the business aspect of the company you're working at, but it is important to try to understand it, talk to stakeholders, talk to internal sort of like domain expertise folks. And so then you'll be better you'll be better able to serve the use cases that the business or your org has. Okay, so with that all out of the way, I wanted to motivate this talk. So as an ML engineer myself, I just wanted to give you a sketch of the life of an ML engineer. So for my umpteenth ML project, of which you kind of work on many, either at your company or in your free time, if you are so inclined, the first step is almost always to get a data set. And obviously step 0 is to have an itch to solve some problem, right? But once you've defined that, you get a data set. You might also make it, which is a little more involved. Typically, you'll just download something from off the web or from some service that already has like a fairly clean data set for you to work with. Then essentially you have to write the training and eval loop, which is essentially, if you're, I'll assume, kind of working with neural nets and deep learning, you write the code that essentially trains, like iterates through batches of your data, updates your model, evaluates your model, so you can test, you can see how your loss or your objective function value is increasing or decreasing over time. So you typically will do this locally on your laptop or maybe on some kind of remote workstation, Jupyter notebooks, etc. And once you have something that you're fairly satisfied with locally, and one caveat here might be that if you're working with terabytes of data, you might get a subset of that data so that it fits on disk, and so you can get that faster iteration loop there. Once you have everything working, all the pipes are running on your computer, you'll then want to scale up and or out. And by scaling up, I mean use a larger machine. Say you want to train like Alpaca or Llama or GPT. You'll need a gigantic instance, EC2 instance or GCP instance for that. Or you want to scale out. So you want to say, train your model on multiple different hyperparameter settings, basically model configuration. And you want to, brute force search or do some kind of random search or something fancier. You want to search that space to find the best configuration for your data set. So you'll experiment a bunch, you'll try a bunch of settings out. And once you have a model artifact, trained model that you're, fairly confident works pretty well for your application, you want to do a bunch of QA. And by QA, I don't just mean the quantitative, like what is your loss or what is your accuracy metric. It's also what is the qualitative behavior of your thing, right? So the most recent example of this might be, okay, I have a large language model now. I want to deploy it, but you want to type some stuff out and see if it says some nasty or silly things, and say you're doing a chatbot for customer service, like you want to further fine tune that if you find kind of aberrant behavior, right? So this is what I mean by QA. And a lot of this stuff is not, it's very much like an art. There's no, at least at this point, there's a certain science to it, but it's actually drawing a lot from my public health background of qualitative research methods. You basically have this magic box that outputs text, staying with this example, and you want to ask it things and you want to interrogate it. Okay, assuming you've gotten here, right? A lot of times, just to set expectations, like 90%, 95% of your models will not make it, see the light of day. But assuming that you have something working pretty well and your team agrees, you'll then want to deploy it. And by deployment, I mean, this could be a batch inference setting, right? So you have a table. Every day I want to take data from that table, use a model to generate predictions, and then dump the predictions into another table. Those are typically for use cases where the latency is in weeks or days or maybe even hours. But it could be also a web server, web API that you hit for some kind of a more live experience, or somewhere in between where it's a streaming thing where the latency requirements are in the order of seconds. Like after 15 seconds, as users put stuff in their e-commerce cart, you want to like process that data to recommend other stuff for them. So it's not, you don't want it in millisecond latency, but so these are kind of roughly 3 modalities of deployment. Then finally, you want to monitor your model. I'll get into this later, but pretty much guaranteed that your model is going to degrade over time. So in production, the state of the world changes, and then now, like pre-pandemic, people were buying certain things. As the pandemic hit, consumer behavior changes, and all recommendation systems are now, bad and need to be retrained. And then there's this never-ending cycle, right? Like for as long as you're at the company, or as long as you're trying to solve this business problem, you're gonna want to iterate on this process. Typically speaking, I don't know if anyone's familiar with the kind of like the buzzword of data-centric AI, but typically speaking, you'll want to iterate on your data set. You can also iterate on your modeling code. You can also iterate on your hyperparameter search. But if we think of models as compressions or representations of the data in a much more compressed format, then the data set is probably something you want to refine. There are probably a lot of mislabeled things in there, et cetera. Okay, so hopefully that's gives you a sense of sort of the general process of an ML engineer. These are now I kind of want to talk about sort of personal insights and insights that I've garnered from my current team at Union AI. These are 3 insights that I think are fairly obvious in hindsight, but are worth just repeating, which is, as I've hinted at, ML pipelines are data pipelines. Machine learning models are essentially, as I said, you can think of them as like data compilers, where data is this raw thing that you have 10 features and you have one target you want to predict. That is you could have millions of rows of this, and these are like instances of mappings from those features to the targets, right? Whereas a model, if I train a logistic regression model, a classifier on the 10 features to predict the one target, I end up with 10 floating point numbers, right? So I've massively compressed the information that was in this data set. Now, logistic regression may not work for your problem. You might want something with higher capacity, predictive capacity. But this is just to highlight the fact that models are essentially data as well. Like if you consider the floats of a neural network, it's just a bunch of numbers, right? So it's not a mind-blowing revelation, but worth highlighting here. The second one is something that I think took me a while to really understand, but just to relay this to you, roughly speaking, we can kind of argue the nuances of this, but roughly speaking, software is stateless and data is stateful. And what I mean by this is, like, say you have an app and you have a bunch of JavaScript code that does, within the boundaries of your problem domain, does a particular thing. Maybe it's a calendar app or whatever. The software itself are just a bunch of symbols in a script that you wrote, right? The data itself that your users are passing in, assuming you've architected this correctly with like a database that stores the state, that all the software layer is doing is kind of ferrying data from the users to the database and database back to the user, depending on the use cases. So this is all to highlight the whole pandemic example I gave you of the state of the world, the underlying state of the world changing, and now the assumptions of, for example, your machine learning model are invalid now. And then finally, related to these previous 2 points, if data shifts, models deteriorate. And so I think I'm just kind of restating similar ideas here, but the main idea is that the only constant in the world is it's changing. And if you have this static model sitting somewhere and it's generating predictions, how do you know, if you're not monitoring it, whether the assumptions of that model that model is making based on the data is trained on is no longer no longer holds today. So next, I want to go into why we built Flyte. And with these insights in mind, I'll kind of go into the challenges of working with data. The first challenge is, say you're right out of school, or even if you have a couple of years of experience in industry, you're starting a new project and you go out and you see, okay, what tools do I want to pick in my tech stack for this project? And as you can see here, this is like out of date by now. I think I screenshotted this last year, but these are all, the high level categories for, aggregation, modeling, visualization. And these are just like a sampling of the vendor / open source tools that are out there. So the ecosystem is always changing. The second challenge is that developing data sets and models is, it could be, if you're not thinking through these things, or you don't have too much experience building these things, can be very wasteful and inefficient. So what I mean by this is, here's like a basic iteration loop, right? I create the data set, train the model, evaluate it. If I'm not taking care of saving or keeping track of all the artifacts that I'm just sloughing off as I'm trying different settings and iterating on my code, I'm going to end up with a lot of uncached, unvalidated data. I'm going to have to recompute the data a lot of times. I'm going to waste a lot of compute. I'm going to end up with a lot of unversioned, unreproducible models. So if I'm not, again, taking care of certain things, I don't know which set of hyperparameters produced the model. I don't know which version of the data set now. So I have V1, V2, V0, I have final version, whatever, like all the problems that you might be familiar with. This is going to be a big problem when you try to deploy, figure out which model you want to deploy. And finally, you're going to have a lot of untracked results. This relates to the model point, which is that each model will have a set of metrics associated with it. And again, if you're not keeping track of these things in a systematic way, you're going to not know which metrics and performance matched which model. The third challenge, and this especially applies in larger organizations, but you can think of this as also a problem with smaller teams and even yourself as you develop something over time, is that ML and data infrastructure doesn't scale well across teams and orgs. And to give you just a toy example here, imagine you have an org with two teams, team A and B, where team A maintains this kind of like critical complex pipeline up here, which might be maybe a data engineering pipeline that produces a data set. Now team A, because they're aware of this, they can update pipeline W and X, and everything will work. But depending on the kind of the level degree of siloing in your organization, which is often the case, team B might not have gotten the memo. They might not have gotten the update that team A has updated this critical piece, and now pipeline Y and Z have broken, and it might be outdated versions or changes in the API or things like that. Challenge number 4, and this I want to call out machine learning in particular, even though some data processing workloads might require these things, is ML workloads require a lot of different things depending on your use case. So you might need GPUs, you might need some kind of cutting edge library that your DevOps team doesn't really want to install in like the main stack, or you want multi-tenancy, you want your compute cluster to have multiple different users and you don't want them to step on each other's toes. There are a bunch of requirements here that I'm not going to call out, but just safe to say that ML workloads have a lot of different requirements that are kind of go beyond a lot of the traditional like software requirements. And then finally, the last challenge I want to hone in on is ML pipelines require dynamism. So instead of a static DAG, directed acyclic graph, you might want your execution graph to depend on the inputs. So this is a good example of this is grid search, where you have the input is the set of hyperparameters you want to train over. And that will, you say n hyperparameter settings, I want n training jobs to run, right? And so this is not unique to ML again, but this is just one kind of good example of this dynamism challenge. So if you're familiar with these challenges, and these are not all of them, there are many, many more actually. There is a category of product called orchestrators, of which there are like a dozen or more at this point. But the orchestrator category aims to solve this kind of complexity and fulfill all of these requirements. So just to give you a very brief background on what orchestrators do, they coordinate the logical flow of computations that are needed to get data from its raw state into some desired state. And this is a very general statement. So the raw data could be a data set. The desired state of the data could be a model artifact that you've trained from it. It could be raw data to process data. It could be raw data to analytics report. But an orchestrator's job is to, just like a conductor in an orchestra, say, okay, you guys play now, you play, and you go. And you essentially coordinate when certain things happen at certain times. So to put all these challenges into a set of requirements, right? If we're going to build an orchestrator from scratch today, there are many more challenges, right? And potentially requirements, but just to stick with the 5 that I've just mentioned. So with a rapidly evolving ecosystem, I want something that's future-proof, that's language and framework agnostic. So if a new library for deep learning comes out, I can like swap out the one component and be fairly confident the rest of my pipeline is going to work as expected. For the data model and development inefficiency piece, it would be really nice to have out of the box support for data lineage tracking, which is as data flows through your pipeline, you know what's the parent node that produced the data, and et cetera, as your workflow and your pipeline kind of becomes more complex and branches out. Also want caching, so I don't, if I give my function the same inputs, I don't have to do the whole computation again. I can just have a cache that I can hit the cache and just output the result of that, assuming that your function is idempotent. So there's no randomness in there. I want it to be immutable, so I want my data and my models to be, in my blob store, my S3 bucket, whatever, for the rest of time. And so I can go back to it. Also immutability with my pipeline code, right? And finally, versioning, where if I deploy a new version and then something breaks in production, I can quickly roll back to the previous version and everything is all good. For the poor scaling across teams problem, would be really cool to have isolated units of compute. So in my graph of like 100 nodes, some of Flyte users have 1,000 node graphs. Each node in that graph has isolated permissions to data, different resource requirements maybe, and the runtime environment, the Python dependencies, the operating system dependencies, all of these are isolated to that one node, so that if I change stuff in there, I'm not going to break anyone else downstream, and I don't have to worry about anyone upstream of me breaking my pipeline. For the infrastructure expertise problem, it'd be really cool to have a declarative syntax for provisioning, for requesting compute, memory, disk, infrastructure requirements. So if I need a Spark cluster or a Ray cluster or a Dask cluster, that as a user, as a data scientist, I can say in my code, hey, I want this thing. And that orchestrator should be like, okay, cool, I'll set it up for you, run your data processing, and then I'll tear it down for you. So you don't run a crazy AWS build. And then finally, for the last problem, the challenge speaks for itself. Like basically, I want an orchestrator that is not just static. It supports some level of dynamism in the way I construct my DAGs. Okay, awesome. So how does Flyte address these challenges? This will be fairly technical, I would say. I'm not going to go too much into the machine learning aspects of this and more into like machine learning systems and orchestration systems. But just to give you a very high level bird's eye view of what happens in Flyte, right? On the left-hand side is some code, not much, but I say import Flyte. From Flytekit, I import task and workflow. I'll get into what these are exactly in a bit. But you can think of workflows as this kind of graph, right? So it's like, here's one node, it outputs something that feeds into other nodes, and then those three are kind of reduced and aggregated in this final node. So I write, imagine just functions that call each other. And then in the Flyte programming model, you package and register that workflow. And essentially there's a compilation step. Flyte is essentially a programming language where we compile that workflow into some representation. Under the hood, it's protobuf, not super important. All I need to know is there's a specification that's language agnostic that can run on any Flyte cluster. Along with that workflow, I also have a container that I've built. So it may be a Docker container, and then some configuration, which is not super important. And the bet that the Flyte team made is that we wanted to use something that was robust and very flexible, also intimidating, but Kubernetes was the answer to this, where Kubernetes is an orchestrator, container orchestration technology, right? So Flyte is built on top of it and adds a lot more functionality to it, but at the base layer, it allows you to essentially spin up pods. You can think of these as isolated containers, and each node, when I execute this compiled workflow on a Flyte cluster, which is actually happening in Kubernetes, each of these nodes is isolated in its own container, its own pod. So that's it. I mean, that's the mental model I want you to take as I describe all the different pieces now. So hopefully you have some kind of tree, some kind of image on which you can kind of hang leaves. So the first core concept of Flyte is the task, and this is the smallest unit of work. You can think of this as a Python function or a function in any other language, with a few things that are different about it. So the first thing to notice is that this function is strongly typed, such that I know what the input interface is and what the data types are, data frames, ints, floats, strings, and what the output is. This is important for type safety. The next point is that these things are containerized. So you can imagine this Python function that lives in a Docker, let's say Docker container, and they're fully versioned. So this is a task. It's essentially the most granular level of compute in Flyte. The way you compose these tasks together into more complex beasts is the workflow. And so as you can see here, this is a workflow that's composed of 3 tasks and then 1 sub workflow. So then this implies that you can call workflows within workflows, which we call sub workflows. Workflows are also strongly typed. So the input output data type boundaries are enforced at compile time, which is an important point I'll get back to later. And data flow is a first class citizen, meaning that this will make sense if you've worked with systems like Airflow and other orchestrators. Typically, you'll have to handle how do I write the output? So if the output of the first task is a data frame, how do I write it to S3? And then if this task is consuming that data frame, how do I read it back into my task, right? So this is not running, this is a distributed system, right? So this is not running on one laptop or one server or one node. This could be happening in various different locations, right? So hence, you need some way of serializing and deserializing your data as it flows through your pipeline. And as I'll show you later, the way Flyte handles this is quite elegant. And finally, their workflows are also versioned. The way that you execute a workflow is through an abstraction that we call a launch plan. And you can think of this as basically just a workflow where you can embed certain default inputs in it. So for example, if I want to retrain my model on certain set of hyperparameters that I found to be good, I can set those as default arguments and then add a schedule so that it can run, say, every week or every day. And the last kind of construct that I want to introduce you to, there are many more in Flyte, but dynamic workflows allow for this dynamism, right? So if my input to this dynamic workflow is learning rate, and I want to give it 4 different configurations to train on, Flyte will be able to dynamically generate the DAG that will then train those 4, and then, say this last task here selects the best one, and then that's the one you deploy. Yes, any questions? I just want to make sure. James? We can do that. We can chat afterwards. Okay. Okay, so you just learned about these 4 constructs, right? Task, workflows, launch plans, dynamic workflows. How do you organize these things together? Flyte has this concept of project and domains, where projects are semantic categories. Say you have a data ETL team, a classification models team. They can all work on the same Flyte cluster, not step on each other's toes, have isolated resource requirements, have isolated data access permissions, all in the same cluster. And domains are a way for you to progress your workflows from development to production. So kind of like a GitOps style, sort of like you merge to the main branch or the dev branch, and then you can deploy, register your workflows according to whatever set of domains you want to progress through. So these are just the defaults that Flyte ships with, but you can really call them XYZ or whatever. So if you're wondering, well, this seems kind of like pretty cookie cutter. So all these features are, roughly speaking, all of the orchestrators have kind of converged on this very similar abstractions. What's unique about Flyte? And the first thing is the type safety opinion. And Flyte is fairly opinionated. So if people don't really care about types, they kind of gravitate toward other tools. But people who have been burned with types not being as they expect them to be, then Flyte would be a pretty useful tool, because so for example, if task 1 outputs a data frame and task 2 takes in a list of dictionaries, at compile time, even before you've run any code, so if anyone here is familiar with like strongly typed programming languages, it's the same benefit, right? You see, Flyte will complain, it'll kind of throw up and say, I can't, this is not a valid thing. Now, within the task function body, a lot of errors can happen because it's just Python, right? So, but at the interface between tasks and between workflows, you will have this type safety feature. Another huge thing that Flyte has is language and framework independence. So today, Flyte has SDKs in Python, Java, and Scala. There's a fairly new one in JavaScript as well, but Python is the most mature one. That's the one that is most maintained, and the core Union AI team maintains. However, because we're working with containers at the most granular level of compute, I can have an R container that has R code, and it can take in the inputs of a data frame. You'll have to hand roll your deserialization and serialization logic. So that's the one caveat there, but you can write tasks in R or Julia or Haskell or whatever programming language you want, or Bash, if you're crazy enough. So language independence is kind of like a future-proof feature of Flyte that, eventually we will probably have some SDKs in other languages, but this is really important in, for example, a lot of biotech use cases where there are just some highly optimized Fortran libraries or highly optimized C libraries for image, for sequence analysis, So a lot of Flyte users can write all their stuff, the rest of their stuff in Python as regular, and then have just one of the tasks be this kind of special case. And finally, not finally, so the second to the last point here of what makes Flyte unique is the declarative infrastructure piece. So I'm not sure This is hard to really explain. You kind of have to experience it yourself to like understand how magical this is. But in a single Flyte workflow, you can have a Spark task and then a regular Python task that uses PyTorch, for example, for model training, and then a Ray task that maybe does some post-processing. And what Flyte will do is it will ephemerally spin up a Spark cluster. You could do your stuff there, as I mentioned earlier, and then it'll tear it down. And then once it gets to the Ray task, it's going to spin up a Ray cluster, do your computation there, and then spin it down. So this is a huge benefit for essentially cost saving. You're not using more than you need. You're not conflating the dependencies of the different tasks in your pipeline. Say the PyTorch task in the middle uses GPUs. I've seen cases of people use other orchestrators and they have a data processing job in the beginning, but the entire pipeline uses a GPU instance, right? The data processing takes 5 hours, the GPU takes 30 minutes, and then they save that model somewhere, and you're wasting 4 hours of GPU time. So these are some of the stories that we've experienced, that we've heard about, that have informed the decisions of this essentially orchestration language. And then finally, this gets to the piece of how Flyte workflows have data flow as a first-class citizen, which is that I'm going to unpack this because this is fairly important. This is probably the most complex slide that I have here. But essentially, this is like a subset of this above workflow, this workflow here. But this is part of the data. This is important for security, essentially. So the Flyte access boundary is this like gray box. I don't know if you can see it. And essentially, Flyte works with a metadata store and a raw data store. And all your raw data, all your data frames, all your tables, all your other stuff, all your model artifacts and pickle files and all that stuff, that lives in your own S3 bucket. Flyte doesn't have access to that stuff. All it has is metadata that are pointers to those things. So if we go here, I don't know if you can see. Let's see if I can get this laser pointer. Oh, nice. So if I have the Spark task, the input to the Spark task is actually a pointer to the raw data. So Flyte never sees the actual raw data, but the task is then able to take that pointer, and assuming you have permissions to this bucket, you can read the raw data in. But Flyte itself as a system never sees your raw data. And so we've taken a lot of care to handle the, again, like offloading of your data into this raw data store and then onloading it onto the next task. And as you'll see in a bit, it's all just Python code, and you don't have to write any of the boilerplate associated with the read and writes for this. Okay, so now I've given you kind of like a higher level conceptual understanding. I'll show you some code now, since this is AI camp. You all want to see some code. So first thing, pip install Flytekit. Flytekit is the Python SDK for Flyte. And we're gonna, just because penguins are cute, I think they're cute, we're gonna train a species classification model. There are basically 3 species in this data set, and the features are certain characteristics like bill length and bill depth and weight, I believe. There's some other features in there. Just to give you a visual kind of reprieve here. This is what the data kind of looks like. You can see the features, and then in the colors and the shapes, you can see the different species. So you can kind of eyeball, based on these features, you can probably fairly well classify these species. So with that model setup in mind, I want to give you a sense of the development lifecycle in Flyte. So the first thing you do is, like with any other project, you import your toolkit. So here we're going to use sklearn, Flytekit, obviously, and pandas for our data. Then we define the task building blocks. So each of these functions are just plain Python functions that I've decorated with the @task decorator. And these will behave just like Python functions. The only thing is, if you have inputs in that function, you're going to have to type annotate them. And if that task has an output, if it has a return statement in the function body, it's going to need output type annotation as well. The @task decorator does a bunch of stuff under the hood, but at a high level, you can think of it as letting Flyte know that these are task abstractions. And yeah, this is a pretty cookie cutter pipeline, right? So I'm getting the data, I'm splitting it, I'm training a model, and then I'm evaluating the model. We stitch these all together in a workflow. So again, the inputs are type annotated, the output is type annotated. At the end, I'm going to return the model as well as the training and the test accuracy. I'll let you stare at this for a little bit as I drink water. So as you can see here, I'm just calling the tasks, right? This is what I'll call the uncanny valley problem that Flyte sort of has. So if I decorate a function with the @workflow decorator, it is no longer a Python function. It is now Flyte's domain-specific language for building a graph. And this is a static graph. This is not the dynamic workflow. So all you can do in this is call other tasks and then pass the outputs of those into other Flyte entities like tasks or workflows. I'm not sure if this will make sense here, and I'd have to kind of like show you an interactive demo that I don't have right now. But if I were to say at runtime, insert like a breakpoint here and access this test accuracy variable, it's not actually going to be a float. It's going to be a promise. And so this promise, there's this promise abstraction where tasks at compile time, they only return promises. And so these are values that are yet to be materialized, and they're abstract. They're going to be materialized somewhere in the cloud and when your Flyte cluster. So that's the one caveat with workflows. So it kind of looks like a function, but it is essentially a subset of the functionality that you might be familiar with. Yes.
Which statements relate to the task previous slide? So like split data with the point of task.
Yeah. So the first thing we're calling is get data. So this is a promise. Then I'm passing it to split data, which then returns 2 data frames, the training and the test split, which are broken out here. I'm training on the calling the train model task on the training data, and then I'm using the model that's output and feeding that into evaluate twice to get the training accuracy and the test accuracy. So once you'll iterate on these 2 parts of the code for some time. With the more realistic examples, it'll be fairly it'll be a little bit more involved. But once you have all of that, you need to build a container. So Docker is one of the kind of most popular container technologies. There are a bunch out there at this point, but this is what a Docker file looks like if you're not super familiar with it. All it says is like these are the steps to build the container that you want to run your task on. So as you can see here, we have some requirements, and then we're copying, this is copying the code into the root directory that Flyte will have access to. Then you package and register your task and workflows to Flyte. This is what the Flyte UI looks like. It's fairly kind of minimalistic and simple to work with, but there are essentially 2 ways of doing this. So you can either call pyflyte run. So pyflyte is the CLI that ships with Flytekit. You can specify to run it on a remote Flyte cluster. You point it to the module and the workflow that you want to run. Or you can say pyflyte register, and then just the directory containing all of your workflow modules. And the first command will actually run your workflow in the Flyte cluster. The second command will just register them. And then you can either run them after the fact, either on the UI or programmatically. So to run it on a console, this is what it looks like. It's a little, yeah, it's a little small. I'm not sure you can see, but the fact that Flyte is strongly typed means that the launch forms that you use to execute the workflows are also strongly typed. So if you try to input a raw string into something that expects an integer, and the Flyte UI will also complain. This is a graphical representation of the DAG we've just created, right? So get data, split data, trains the model, and then the output of that is fed into evaluate. So this is literally a visual representation of this. There's a bunch of metadata, and like you can see the inputs and outputs of your task. So here we're getting like a 99% training accuracy, which makes sense since this data set is pretty small and known to be easy to classify. And you can schedule your workflows with launch plans. So this launch plan abstraction I told you earlier allows you to take in the workflow that you want to run on a schedule, specify a cron schedule for it, say to run hourly, and then embed some default inputs into it, like the hyperparameters. You can visualize inputs and outputs of your task with abstraction called Flytedex. And essentially, you need to add some arguments to your add task decorator. Disable deck equals false. And then you call this deck class and provide a renderer for it. So this is a renderer that ships with Flyte. That's basically the pandas profiling renderer. And in the UI, you will see a Flyte deck with the output that's sort of a summary of your data set, and it'll give you some visualizations as well of your data set. And you can customize these super easily too. So this is literally the code for creating a confusion matrix with of the model predictions. So once you've built your workflow and your task and it's kind of humming along in your cluster, there are a bunch of ways that you can optimize your workflows. And this is kind of like the scaling up and out piece and reducing the inefficiencies. So one way you can do this is by saying cache equals true at the task level. What this will do is your train model task will run once and then cache the output based on the inputs you supplied here. And if I give the same data frame and the same set of hyperparameters, I'm not going to retrain the model. I'm just going to hit the cache again and give you the output of that. So for model training, this is great. For data processing, this is great. If I have the same query with the same parameters, SQL query, the same parameters, I'm not going to have to burden the actual database server for the query again. Flyte is just going to keep an intermediate output of that somewhere in the raw data store. And so it's just going to grab that again. You can scale out with map tasks. So if you're familiar with the map abstraction in Python, you basically take a function and you apply the function to elements in an iterator or iterable. This is a similar kind of abstraction where if I want to do grid search, for example, I take my train model task, I wrap it with map task. I say concurrency equals 5, meaning I only want 5 tasks running at a time. And then I give it this prepare train args task, just gives me a list of the hyperparameters. And this is essentially the syntax for you to massively parallelize this. So there are companies that have concurrency of thousands, and they run map tasks for data processing and model training. And yeah, this essentially gives you like the superpower to parallelize anything by like crazy degrees. Oh, go ahead. Yeah, so the complexity that I've sort of intentionally ignored in this talk is setting up your Flyte cluster, which is fairly involved, to be honest. But you essentially need a AWS account or GCP account. And there are a bunch of Terraform files. These are files that allow you to specify infrastructure and spin up infrastructure. The open source team maintains a few of these files, and this allows you to stand up a Flyte cluster. And once you have that cluster up and running, Flyte will handle the rest of this. But under the hood, it's all using Kubernetes to spin up all the containers and the processes to run this map task. This is also a more generalizable lesson. Many other orchestrators have a similar construct, and some other frameworks like Dask or Ray, they will have their own kind of map type abstraction to do this. Yeah, that's correct. Yeah, correct. So for AWS, that would be GKE or EKS, and for Google, it would be GKE. Yeah. Here's an example of scaling up, where this is the PySpark example. When I mentioned the term declarative infrastructure, this is what I mean. So all the user has to do is say, hey, in this task, I want to run it on a Spark cluster with this memory, 1,000 megabytes, 2 instances, 1 driver core, a bunch of other configuration there. But essentially, the function body of this function, preprocessed data PySpark, will execute on an actual Spark cluster that Flyte provisions for you. And then another example that's a ML workload. This is a Kubeflow PyTorch example, where if you want to do distributed training, so I'm training a model on multiple nodes, and PyTorch handles like the distributed training for that, so you don't have to worry about it. But what Flyte gives you is the ability to say, hey, I want to run this PyTorch job on 2 workers, 2 instances, and I want to request a GPU, 2 CPUs, and 1 gigabyte. And this is how you ask Flyte to get these resources for you. It'll spin up the required instances and then tear them down once you're done with them. So I just threw a bunch of concept at you. I hope some of it will kind of stick in your mind. But to give you some concrete use cases of how companies are using Flyte today, I'll just mention 4. That gives you kind of a breadth of the different kinds of use cases here. So Spotify uses this as more of a financial forecasting tool. So they have an end-to-end profit and loss forecasting use case, and they use Flyte. I think they have tons of executions per day. They've scheduled a lot of batch jobs here, and it's helped them increase their velocity for delivering these models. And as I mentioned earlier, it also breaks down the silos between teams and allows them to sort of reuse each other's components as they need to. Freenome is a company that does early cancer detection. Excuse me. And Flyte is one of the main workhorses for this use case. We don't know too much about what they're doing. Obviously, it's proprietary stuff, but safe to say they're using this for getting a bunch of data in the lab, other data sources, and they're essentially doing early cancer detection using Flyte. Black Shark AI, this is a company I think that started in Microsoft that was spun off, but they're essentially making a 3D map of the world using satellite imagery and a bunch of other data sources. I'm not sure, but they crunch through 2.5 petabytes of data. They use Flyte. And essentially, it's no machine learning there, I don't think. But they go through tons of data to create these 3D maps. And finally, Gojek. This is rideshare company in Southeast Asia, South Asia, or East Asia that uses Flyte for price optimization, ride matching. Flyte actually started at Lyft, so this is kind of a very familiar use case for us. So to summarize, Flyte orchestrates data, compute, and infrastructure. This is something that not all orchestrators will do, especially the last piece. It provides type safety, meaning that you can catch compile time bugs early. It has container native tasks at the most granular level of compute. And this gives you a lot of benefits, including reproducibility. I have my container. I know what code is in there. I know I can inspect it. If something goes wrong, I can reproduce the error. You can scale your production workflows really easily. With the examples I just showed you, you essentially declaratively say what infrastructure you need. There's some communication you need to do with the admins of the Flyte cluster. So there's no getting around that today. But once those are set up, you can ask for GPUs to your heart's content and not have to bother your DevOps team. Supports a canonical data science and ML stack. So it supports PyTorch, TensorFlow. There's a Hugging Face integration. There are a bunch of, there's an ML flow integration. So there's a bunch of integrations that we've built out over time. If none of the existing functionality works for you or your particular use case, you can easily extend it and customize it. And finally, I think most importantly, it breaks down the silos between data and model teams. These are a few quick resources you can use to get started with Flyte. Excuse me. And so there's docs.flyte.org. You can join the Slack community. We're always in there helping folks onboard. And the code is in GitHub. Just want to give a quick shout out, shameless plug. So Union AI is essentially commercializing Flyte. So if you don't want to worry about the infrastructure setup for Flyte, you can use Union Cloud. So just a quick plug there. We're also hiring. You can go to union.ai/careers. You can see we're hiring for developer, marketing, and sales positions. Excuse me. Oh, mouth is really dry. Throat is really dry. And yeah, you can get started. You can pip install Flytekit and call PyFlyte init my app to get started. Thanks so much.
On your Union product, what's your typical market size of the company you're trying to, or you're most likely to talk to?
So as a startup, the answer to that question is kind of everyone, but our main focus is we have customers and prospects of very different sizes. So we have very large international companies like with teams across the world. We have smaller startups as well. We have kind of mid-sized kind of biotech and pharma. Interestingly, biotech and pharma has been one of the customer profiles that seem to like Flyte for whatever reason. So, but in terms of size, it kind of runs the gamut. So Union Cloud is cloud agnostic. So that's kind of like one of the other benefits of Flyte is it runs on Kubernetes. So that's kind of like the constant. But any cloud platform that supports Kubernetes, which is a lot these days, essentially you have to create a cluster, provision like a Postgres or SQL database and a blob store like S3
So
or
it's not like a SaaS model where you go in the marketplace and buy it.
yeah, it's not like that. Again, at least today. Awesome. Well, yeah, I'll stick around here if you want to chat and
Yeah, I don't
You
know if anyone trying to teach or like add the models. We have a keyboard base, so there is still time if you want to tweet with the hashtag.
Do you have a copy of the presentation?
sure. Yeah, will this, can I share the slide somewhere? I can send it to you. Okay, cool.
Send it to the info.a, send it to Bill and he.
Awesome. Cool. Great. Well, thanks so much for your attention. I hope you learned something.